Hi, my name is Andrea Schmidt, and I'm a data scientist and a recent graduate from Galvanize's Data Science Immersive program. Prior to the program, I worked in manufacturing and operations, and I also hold a Bachelor's of Science in Industrial Engineering. Today I'm going to talk to you about the problem of Austin's decreasing ridership and how machine learning can be applied to solve it. So why do we care that public transit ridership is down? Because Austin traffic is getting progressively worse every year. Today we have upwards of 400,000 commuters on the road every day, with 33% of them starting their commute from outside of the city. So what's going on with Cat Metro? According to their recent report, overall system participation is down 4.8% month over month for January. So my thesis is that the system is not useful because the routes are not where they should be. I asked Homer this question, and he didn't know. So good thing that Lisa was nearby. And I learned that the transportation industry calls this the transit network design problem. And it's a continuous area of study, especially in countries like China and India, where population challenges are at much greater scale. I also learned that academics are trending towards using what's called evolutionary computing to solve this problem. So what is evolutionary computing? It's an AI technique that is particularly useful at searching large solution spaces. And what makes these algorithms so cool is that they mimic biological natural selection, where solutions compete against one another in a battle of survival of the fittest. So I decided to build one and use it to solve Austin's decreasing ridership problem. This is how the algorithm works. First, random selections compete against one another, revealing a set of winning solutions. Then we randomly mutate that set, we randomly mutate a portion of that set, and then have those mutant copies compete against their original versions. At the end of an evolutionary cycle, we have an optimal set of solutions that we can choose from. So the core of the algorithm relies on three main functions, which is the random selection, the fitness function, or our performance or scoring method, and then an evolve or mutation function. For my project, I'm using the typical stack of Python data science libraries, but I needed to find a way to read shape files. So I worked a lot in GeoPandas, which is a version of Pandas built with Shapely and Fiona libraries to more easily work with geospatial data. To the left, we have our current fixed route system with the red dots indicating locations of bus stops. You could see huge underserved pockets in this system. It sticks primarily to the main roads and intersections and failing to get into the neighborhoods where people actually live. To the right is my proposed network, determined by using a k-means clustering algorithm based on population density and initialized with the same number of clusters as there are current bus stops in the system. So I'm going to use these points to design my regional routes, and this brings me to talk about strategy. Our greater strategy, or the greater strategy I'm going to be using, is to layer a localized fixed route system on top of a rapid transit linking system. But for the purpose of demonstrating model effectiveness, I'm just going to focus today on building a route optimization algorithm for one small area of the city. Let's look at the east side of Austin. And I randomly selected a subset of potential bus stops and arbitrarily chose the location of a transfer station on the far west end of the region by the purple star, close to freeways and the downtown district. I also specified that I want to build two routes for this area, both originating from the transfer station and culminating at two specified nodes on the far east end. So now that we identified where the stop should be, how many routes to make, and the location of the start and end points, we can run the algorithm for 5,000 random selections, and we're going to define fitness as Euclidean straight line distance between those nodes. Okay, this is pretty pretty cool. You can see here we have 4 solutions with similar fitness scores ranging from 0.22 to 0.24. So now let's take these 4 routes and run them through 50,000 evolution cycles. Now this is interesting because the fitness scores improved dramatically, and it even yielded 2 sets of identical routes originating from 4 different parent routes. So this tells me that my model works and behaves as expected. So just how well did the model work? Pretty darn good. Evolution performed 20 to 30% over random selection. I'm pretty excited about this because it tells me I have a viable method for designing routes now. So what's next? Now I need to redefine my fitness function, and I need to take into account the multiple paths a vehicle can traverse to get from one node to the next. I'm thinking of employing an A-star graph search and weighing the edges or paths by average traffic flow speed. And after that, I can evaluate the full set of data on a remote server, do a high number of random selections and evolutions, and see what I get from there. Then I'll have a pretty cool tool I can share with Cab Metro. If you're interested in this topic, feel free to reach out to me. This is really well documented and complex problem with a great deal of research behind it. You can also find me on GitHub, where you can follow my progress and view the details of the model that I built. Thank you.